What if you could count how many 1 bits are in the binary representation of every number from 0 to n, in just a split second? Counting bits is a Pattern Mastery 100 in LeetCode favorite because it tests if you really know how to optimize with dynamic programming and bitwise tricks. This problem pops up in Phong interviews and is a launchpad for mastering binary manipulation and efficient array filling. Ready to turn a brute force grind into a one-pass breeze? Let's get started. Let's break it down. You're given a number n. Your task is to return an array. Each position I in that array should tell you how many ones are in the binary form of the number I. For example, if n is 2, we look at the numbers 0, 1, and 2. 0 in binary is 0b0. It has 0 ones. 1 in binary is 0b1. It has 1 1. 2 in binary is 0b10. It also has 1 1. So the final array is 0, 1, 1. Now let's assess our options. A naive approach would use a helper function like bin I. Count 1 for each number from 0 to n. That works but is O(n) log at time. Can we do better? Yes. There's a dynamic programming trick. For any number I, the count of ones is 1 plus count of ones in I and I1. Or, using another pattern, count bits I equals count bits I right shift by 1 plus I and 1. That's because shifting I right by 1 drops the least significant bit, and I and 1 tells you if that dropped bit was a 1. This lets us fill the answer array in O(n) time. Here's the structure. Initialize an answer array of size n plus 1 with zeros for every I from 1 to n. Use ens I equals ens I right shift by 1 plus I and 1 to fill in the value. Return the array. Let's try to implement it using solution 1. Since this loop runs n plus 1 times, the overall time complexity starts at O(n), and inside it, we'll do more work. We start by defining a function called countBits, which takes a number n. Our goal is to compute the number of 1 bits for every number from 0 all the way up to n. We create an empty list called res. This is where we'll store our results, one entry for each number from 0 to n. Now we loop from 0 up to n, inclusive. For each number I, we're going to count how many 1 bits it has. This comment reminds us what the next few lines are doing, counting the set bits of the current number. We take the current number I and store it in a temporary variable x. This allows us to modify x bit by bit without touching the original number. We initialize a variable called count to 0. This will track how many 1 bits we find in x. Here we start a loop that continues as long as x isn't 0. In each step, we look at the least significant bit. We check the last bit of x using x and 1. If the last bit is 1, we add 1 to the count. It's like checking the rightmost light in a row. Is it on? Then count it. We right shift x by 1 bit. This discards the bit we just checked and moves the next bit into position. It's like sliding a magnifying glass across the binary digits. Once we've checked all bits of I, we append the final count of 1 bits into the res list. Now we have the Hamming weight for this number recorded. Finally, after we've processed every number from 0 to n, we return the full list of results. Each index tells you how many ones appear in that number's binary form. Solution 1. Case 1, n equals 2. Let's test our function using this input, 2. This value represents the upper limit. We're computing how many 1 bits appear in every number from 0 all the way up to 2. Here's why the solution works. For each number, we shift through its bits and count how many are set. 0 0 bits. 1 1 bit. 2 1 bit, 10 in binary, so the final array becomes 0 1 1. And that's exactly what our program outputs. 0 1 1. The code is working correctly and passes this test case. We'll now walk through solution 2, the dynamic programming version. We start by defining a class called solution. This is just a container, like a folder where we neatly store our bit counting function. Inside the class, we define a method named countBits. Its mission is simple. For every number from 0 to n, compute how many ones are present in its binary representation. Here we initialize a list called res with n plus 1 zeros. Each index in this list will eventually hold the number of set bits for that number. Now we start a loop that goes from 1 up to n. We skip 0 because we already know its bit count is 0. This loop runs n times, giving us an overall time complexity of O(n). This comment explains the key idea behind this algorithm. The number of 1 bits in I is the number of 1 bits in I shifted right by 1. That's removing the last bit, plus 1 if the last bit of I is a 1. It's like saying, count the bits in everything except the last digit, then add 1 if that last digit was on. This is the line that makes the whole algorithm efficient. We take res I1, which is the bit count of the number without its last bit, and then we add I and 1, which checks if the last bit is a 1. Just 2 operations. No repeated bit scanning. No extra loops. This is dynamic programming at its cleanest, building new answers from previous ones. Finally, we return the list res, which now contains the bit count for every number from 0 all the way through n. Simple, fast, and ready to use. And that's how this algorithm works. It first creates a results list pre-filled with zeros, then fills each entry using a clever dynamic programming relationship that reuses previous computations. Efficient, simple, and elegant. Solution 2. Case 2, n equals 5. Now let's run the function with input 5. Again, we're calculating the count of set bits for every number from 0 through 5. Using the same DP rule, we compute each value. 0 0 bits. 1 1 bit. 2 1 bit. 3f1 plus 1 equals 2 bits. 4f2 plus 0 equals 1 bit. 5f2 plus 1 equals 2 bits. So we end up with 0, 1, 1, 2, 1, 2. And our program outputs exactly that. 0, 1, 1, 2, 1, 2. Perfect match with the expected results. So, our implementation is correct. The algorithm successfully computes the number of set bits for all numbers from 0 to n using efficient dynamic programming. Fast, accurate, and reliable. Let's wrap things up. This problem was all about counting bits efficiently, not just for one number, but for every number from 0 up to n. Breakdown recap. We started by understanding that for each number, we needed to figure out how many ones appear in its binary form. Essentially, we're building an array that shows the bit count for every integer in sequence. Assess recap. We compared two ideas, the brute force way using built-in binary counting, and a smarter dynamic programming method. The DP insight was that the count for any number I can be derived from smaller results, either by using I and I1 to remove a bit or by noticing that shifting I right gives us a related subproblem. This transforms a repetitive process into an ON solution. Structure recap. The plan was straightforward. Start from 0, and for each number, calculate its bit count using previously stored results. This lets us fill up the arrays step by step without recalculating from scratch. Implement recap. We coded this solution on LeetCode, and it executed smoothly without any syntax or runtime errors. Check recap. After running the test cases, the output matched perfectly across all inputs, confirming that our dynamic programming approach worked exactly as intended. The big takeaway? Bit manipulation and dynamic programming make a powerful combo. When you spot patterns that build on smaller subproblems, you can turn what seems like a heavy computation into something beautifully efficient.